This lesson. This is the remainder and factor theorem. We're going to take a look at both of these theorems, one of which is a corollary to the other, like a result of, or another way of writing the other theorems. So let's start with this first example here. Determine the value of f of 3 by using direct substitution. And then the second part says determine the value of the remainder if f of x given above is divided by x minus 3. Okay, x minus 3. So let's do part A together. What does direct substitution mean? It's not fancy. It means exactly what it sounds like. What should you do, Hannah? Directly plug it in or directly substitute. Absolutely. So f of 3 means 3 times 3 cubed minus 2 times 3 squared minus 4 times 3 plus 5. So again, 3 gets plugged in all of these spots where you see an x in f of x. Okay, I plug in all these values. I'm going to get 81 minus 18 minus 12 plus 5, giving me a total of 56. Again, check your math, please. Here, be careful, be careful. Even if this number were negative here, you still have to put the negative on the outside here. Because some students are like, oh, negative squared makes that positive, so it's positive. No, this negative is still out here. And this is squared itself, this is cubed itself, the sign is applied afterward. How could you obviously get this number much quicker, especially if you needed many results? Like what if I wanted, ready? I want f of 3, f of 5, f of 7, f of 9, and f of 12. Do you want to do this 5, 6, 7 times? So what do you do to make it a lot quicker? How would you do this quicker? Okay, well, use your tools.
I don't know, long division?
You could possibly, we're going to see that today, but let's hold off on that statement because you're kind of jumping ahead on us. So we're going to use long division or synthetic division.
Yeah.
What do you have that helps you sometimes calculate things pretty quick?
Calculator.
How do we do this quicker on a calculator? Who knows? Who remembers? We've done it, right? George? No matrix needed.
You do you graph it as a line, and then you do find.
Close. We were halfway there. You input it into y1, so you had the right part first. You just find the graph. You don't have to actually graph it at all.
I don't know if I'm right. I'm just guessing. But do you already plug in the numbers for that? You just plug it in and you compare it. Something around there. Like you plug in the numbers when you put it into y equals.
Close. I would still plug in the function, but I'm going to plug in the numbers. But where am I going to plug in those numbers? To make it nice and quick and get all those y values. Where am I going to plug the numbers in? Along with the y values, I'm plugging in the what values? So what do I plug them into on the calculator? What's that called? What's it called on your calculator? Top right button, Max. Top right button. Second one. Table. You plug it into a table. Right? So in your calculator, if you needed to find the value of 7 y values, you would not do this substituting directly 7 times. It makes no sense whatsoever. So just to clarify what I'm talking about, I'll put part B at the end. Forget that for a second. You'd go to y1 first. You'd input the original function. Okay, that goes into y1. 3x carry 3 minus 2x carry 2 minus 4x plus 5. I'm writing it the way you would type it in y1 in your calculator. You could do this if you want right now to practice, but if you know what I'm saying, by all means. But nobody seemed to answer, so. Then, if it were me, I wouldn't even go to my graph. This is a cubic function. We're going to talk about graphs of polynomials in another section later in chapter 8. But for now, what do you think about the shape of this? What I want you to think about is, if I asked you to find out the values of f of 3, f of 5, f of 7, f of 9, f of 12, f whatever. I'm picking a lot of numbers on purpose to make it annoying. But say I wanted you to find all 6 of those values. You're not going to use direct substitution 6 times. Please. Go to your calculator, type that in y1, then press second table. So then on your calculator, it brings up a list of x here, and then it says y1 right there. And what are you going to type in right here for x? You're going to type in all of these numbers. If your calculator isn't set up that way, it means you didn't listen when I told you to change the settings. To do that, to do that, you go to table settings. Press second, table settings, and you change the independent variable to ask instead of auto. Instead of automatically putting in numbers here, you can ask the calculator for values of y1 given these values you're directly inputting. Okay, so again, that's the approach you would take on a graphing calculator. Next time we do this, guys, take out the calculator when I start talking about it, right? So that you're not like now doing it suddenly. Practice doing it real quick if you want. Again, this goes in y1, right here. Press second table and type in these numbers, and you'll get the answers. If you can't type in these numbers, it means your table is not set up right. You got to press second and go to table settings and change independent to ask. Change the independent variable setting to ask instead of auto.
Wait.
Second, table settings, right next to graph. It should be one of the second commands on the top row, table settings.
Window. Just hit
Second window. And then go to independent, change that to S. Now go back to your table there. You'll see that the X column.
enter. How do you hit enter from it?
Please ask if you don't know. Can you start to ask?
I think I left it on because like, oh, it's right
Second
there.
graph. Second, and then graph, table, and then table. Now you can just type in the numbers and do 3, enter 5, enter 7, enter 9, enter. What's in Y2? Okay. Something's in Y2. In Y. Okay, so that's clear. Put it out clear. Also, I would type in the original function. 3x cubed, x 2x squared. See that there? So you're not going to use alpha for x actually. X is right there. That's the independent variable. And then you want cube. Do you like having it go up like that? You like to see that? Okay. It's called magic print. If you're going to do anything with computer coding, though, you should get used to doing it like this. See the little caret I'm showing on mine? If you change those settings, it'll show a caret actually. Anyway, but continue typing it in and then go back to what the table is. That can come, and then go to it takes you to the error. Second. I'll tell you the numbers. 3, 5, 7, 9, 3, enter. 5, enter. 7, see what I'm saying? It's a much quicker way to get one. How many sides are in? Well, there's another change.
Wait, I think that are not the same. No, that's the
This is the original. If you go one, this is not x to the third. This is x to the.
Stop touching my stuff. That's
Oh, you just took the whole thing?
I'm crazy.
What you did was you went to table settings, and I think you. Let's see where your table settings are.
I'm right.
Maybe you did that.
No, no, no.
Right. Always correct.
No, like, because there was
No,
no.
Oh, because nothing's there. You have to have a function.
But I'm not.
So I just put it like here, X.
After the step.
I'm not wrong.
Because it's taking the X values and plugging in these other functions here. So you need to have that function written there.
I didn't.
That's fine. You have 3, 9, and 5 written down. Those numbers there in blue. You need the actual function for Y1 and plugging into it. That goes there. So this is like f of x. This is f of x.
I did the actual number. Didn't know how to do it. But I did the actual.
Forget the steals. There's second.
Yeah, I get it. She made it clear.
Now you just type over his x values.
Oh, you're so sorry.
Makes sense? You got it? That? You good, Rich?
My calculator died.
Did you stand up? You're good with the calculator. That's why the calculator. You sure?
I can try.
Figure it out?
Are you sure?
These are y values. So these are ordered there, right? So guys, please remember that when you evaluate a function, the answer you get is an ordered pair. So 56 should go in this first spot. I'm hoping you all got 56 here, right? So that means that a point on this graph is 3, 56. That's a coordinate on the graph. It's a coordinate on the graph there. All right. Now, with that said, let's go to part B. Determine the remainder of f of x when it's divided by x minus 3. So if you're dividing the function by x minus 3 and you're doing synthetic division, I'm going to do synthetic. It makes more sense. What goes on the outside when I'm dividing by x minus 3? Everybody.
3.
Yeah, it's just positive 3. Yes, go for it, Max. Then along the top, we're going to plug in our original values, 3, -2, -4, and 5. Okay, so those are the coefficients. Where do those numbers come from in red? To make sure we're clear, look up at the top here. Let's see if I can zoom out a little bit. Yeah, there we go. So these numbers up here, all these numbers up here, 3, -2, -4, and 5, the coefficients are going right here. And since we're dividing by x minus 3, we put a positive 3 on the outside. Let's go ahead through this table and do this. We bring down the 3 to start. 3 times 3 gives me 9 plus -2. 3 times 7 gives me 21 minus 4.
17.
3 times 17
51.
plus 5.
56.
Look at that. Convenient? Coincidence? I think not. It's definitely not a coincidence. That's right. Very good. I was waiting for somebody to say that. So, this coordinate is occurring when we do this with synthetic division also, which is mind-blowing. Well, what we call this is really the remainder theorem. The remainder is the y-coordinate. Write that down in big letters. The remainder is the y-coordinate, actually. Another name for this, besides synthetic division, is called synthetic substitution. You're going to hear me say that a lot now. Instead of direct substitution like you did with part A, synthetic substitution is a whole lot easier. If this polynomial was to the 5th degree, you'd have to do 3 to the 5th with direct substitution. Here, look at that. No need to work to the 5th power. Nice and easy. So the y-coordinate of a given point is represented by the remainder. The remainder. And actually just had a mind-blowing breakthrough, so make sure you catch up here. The y-coordinate, Max, with synthetic division is really just the same thing as the remainder. So when we took a 3 and plugged it into the synthetic substitution, we divided by x minus 3. If you plug a 3 in, it turns out that your remainder is the same answer you got from doing direct substitution. So this remainder is really just the y-coordinate, and this here is really the x-coordinate. Yeah.
Isn't the remainder though 56 over x minus 3?
No, that's the fractional part of the answer, of the quotient. But that's the remainder itself is just 56. Remember? Like with long division, when you did 56 divided by 5, the remainder was 1, not 1/5. The fractional part is 1/5. The remainder itself is just 1. So the remainder is always the y-coordinate. Now, let's go back to what Hannah said. Hannah said if the remainder is 0, then we have a factor. Think about that for a second. This is going to lead us into the next theory. If the remainder is 0, what does that mean about the coordinate? It's a x-intercept. And x-intercepts came from factors, didn't they? It's all connected, all this stuff we're doing. Again, if you got 0 here, it means this coordinate is 3, 0. Where's the coordinate 3, 0? It's on the x-axis. It's an x-intercept. And x-intercepts always came from factors. That's why Hannah mentioned that this was going to be something to do with factors when that's a 0. Okay, so let's carry that into our next example here. Okay, let's carry this into it. Now again, though, this is the remainder theorem we're looking at right here. The remainder theorem, that the remainder is the y-coordinate. The remainder is the y-coordinate. That's the remainder theorem. Another name for this is synthetic substitution. So here's our corollary. Here's our corollary. We call this the factor theorem. This is exactly what Hannah mentioned. The polynomial f of x has x minus c as a factor if and only if c is a root of the equation. Well, when it's a root of the equation, what is this really saying? In layman's terms, this is saying if I do this and get 0, it means that x minus c is a factor. If I plug in whatever that value is and get a 0 as a y-coordinate, I plug in x, I get to 2 here for c, and I get 0 out for y, it simply means that whatever that c was, x minus c is a factor. And that's true because, oops, that's not how I write because c is a root. Again, when something is a root, it means when you plug it into the function, you get 0. We call it a root of the equation, or a 0 of the function, or the x-intercept of the graph. Pretty much when you plug a number in, if you get 0, you get an x-intercept, a root, whatever it is. That's why x minus c is a factor. Okay, that's why x minus c is a factor. Let's look at an example of sense of this. If x plus 4 is a factor, hey, you're told right away it's a factor. So what's your remainder going to be?
0.
Your remainder's got to be 0 in this problem, right? It's got to be 0. So if you're told that x plus 4 is a factor, find the other factors. Okay? And then it says, based on the other factors, what are the zeros of the function? So let's go through this process here. Up top, I've got 1, -5, -22, 56. Outside, I've got a -4. Again, why am I allowed to put a -4 there? Because if something is a factor, it means that if I divide by it, it'll divide evenly. So really this problem is telling me, you know what? Divide by x plus 4. If I'm dividing by x plus 4, I'm really just putting a -4 out in front. Another way to think about this is as follows. If something is a factor, what's the root? What's the root? If x plus 4 is a factor, what is the root that makes the polynomial 0? What is it? Just -4. Remember, the root is always the opposite of the factor that we had there. We did that when we got to like a t-chart at the end of a problem, when we factored. So if I were to take this expression here and factor it into other expressions, I would end up with x plus 4 and then something else. Now, that something else is going to be a quadratic to give me x to the third. So this will be something x squared times this will give me something x cubed. So I got to figure out what that is. So let's go ahead and bring it down. Bring down the 1. -4 times 1 is -4. -4 and -5 is -9. -4 times -9 is 36. 36 minus 22 is? What do you got? -4 times 14. What do you think it's going to be? -56. And then when you add 56 to that, 0. It's not a coincidence. Not a coincidence. Now, if this is the case, you recall, what should the degree be for this next expression that I'm going to pull down from these 3 numbers? What should the degree be? Kate? Yeah. It should be second degree. Can somebody explain again why that is? Why is this second degree here? Why is this second degree? Rich?
Isn't it because when if you're going to multiply it by x again to get the original equation?
Yeah, you get back to x to the third. Very good. Okay? So Bridge noticed if we take this quantity and you're going to multiply this by x plus 4 anyway, it's going to get you to a cube or cubic expression. So really this thing goes in here. That's the factored form of f of x. That's what this problem is giving us. It's giving us the other factor. Well, x plus 4 was one of them. This is the other. Can I factor this further?
Yeah.
Annette, what do you think?
Well, you can make x squared, the x squared minus 9x, you can make it x minus 7x minus 2.
X minus 7, x minus 2. That was way too big of an erase. Do others agree with that? Does that make sense? You got all the factors, right? From the original one, this is quadratic here. Now, if that's the case, what are the zeros of this function? What are the zeros? -4, 2, and 7. How do you find the zeros of a function? You set the function equal to 0. And then make your little t-chart. Each of these factors could be 0. So this is what the t-chart would look like. X equals -4, x equals 2, x equals 7. Those are the roots of this equation, or simply the zeros of the function.
So would problems like, so would this be used to like answer like is x minus whatever a factor?
Yes, very good. A question I could say, is x plus 2 a factor of this? What do you look for? 0 is the remainder. If you get 0 as the remainder, you know it's a factor. If x plus 4 is a factor, you know one of the roots will be x minus 4. Remember, when something is a factor, it means that one of the roots is usually the opposite of that factor. Okay? Again, and I mean that because you set it equal to 0 to get the roots or the zeros of this function. So if you were to take a 2, and plug it in out here, what would your remainder be?
0.
Why?
Because it's a factor.
Because x minus 2 is a factor, right? Because x minus 2 is a factor, if you plug in a root, which is 2, you'll get a y coordinate of 0, wouldn't you? Think about what roots mean on the graph. What do the roots really mean again? They mean x-intercepts, right? So what this means is that this graph has coordinates as follows. And we're not going to really get into this too much in this section right now, but when we get into a later part of chapter 8, we're going to do a lot with graphing. And this is going to be extremely important to recognize that these coordinates are really x-intercepts. And they always give you 0 as a remainder because the remainder is just the y value. Okay, it's all connected. It all comes back together.
Do you know who invented this theory?
I don't. Isn't it amazing though? So let me tell you a little interesting thing. When I was in high school, I never learned this. We never did synthetic division. We never did synthetic substitution. So I started teaching math, specifically. I started teaching in general about 9 years ago. And the first year I taught Algebra 2. And this was a new topic even to me. And I was like, wow, this is pretty amazing stuff. And it actually works out this way. I used to always have to do it by hand. We would try like with long division the whole time. I never did synthetic substitution ever. It just wasn't a thing. I don't know why. And there's a lot more than just this we're going to see in a little while. Turns out, George, that there's even more reasons to this. If the signs here alternate, or if the signs are certain ways, it means something else altogether. See how these signs are alternating? Positive, negative, positive, and then just 0? The fact that they're alternating represents that this is called a lower bound. And all the other roots have to be greater than -4. Look at your other roots. Weren't they both greater than -4? It's kind of amazing. There's a lot more to synthetic substitution than just that. It's kind of like creepy crazy, you know? You're like, how does that work out, you know? But it's true, actually. That's actually interesting. I should look it up a little more. I honestly, never took the time to figure out like who invented it or why it came about. But maybe you can figure it out for us. I don't know. I'm curious.
If you were to graph this, what would it look like? Would it be like a squiggly line?
Yeah, so here you go. Just plot those on the x-axis. Here's -4. Here's 2. Here's 7. We're going to talk later about something called end behavior. I know that because this was a positive cubic, it's going to go like this. Like a line would go positive with a slope. So it's going to end up like this. It's going to go up like that. It's going to go up like that. And then this is just going to go. Whoop. Now, the curvature here depends on the function more. I'm like guessing. I didn't put y values. You notice that? But I can get the y-intercept from the original. The y-intercept is 56. You see it up top? The y-intercept is 56. So this would be a very high height here. This would be where 50 is on that axis. That make sense? We're going to do a lot with graphing of this. It's good to see it right now because you get an idea of what you're doing. We're going to do a lot of this in another section in chapter 8. Okay?
This is like, is this the thing with like tangents or not?
You mean, there's a lot of stuff with tangents. We're gonna use tangent lines at a certain point. A lot of things in math relate to tangent stuff. Points of tangent C maybe where you have like double and triple roots too. Let's take a look at this one. If x equals 1 as a root, then find the other roots. Well, if x equals 1 as a root, what was the factor that gave you x equals 1 as a root? What was the factor to give you that as an answer? What factor must you have to get 1 as an answer? X minus 1. X minus 1 must be a factor of this then. That must be the case. Well, if you don't believe it, you can test it. But anyway, you're going to test it either way. So let's plug a 1 in. Notice I plug a positive 1 in because the factor was x minus 1. So I can pretty much take whatever the value is that is the root. In this case, x equals 1 is the root, it says, and plug in the 1 right away. Remember, factors, you're going to take the opposite of whatever the factor is. But if the root says it's 1, just take the 1 and plug it in right off the bat. So now we bring down the 1 from the top. 1 times 1 is 1. 1 plus negative 4 is negative 3. 1 times negative 3 is negative 3. Negative 3 and 15 is going to give me negative 18. 1 times negative 18 is negative 18. Plus 18 is 0. It's not a coincidence. Again, is that clear? It's not a coincidence. We then go ahead and take the next equation from this. Bring these down. I know that this is x squared because I started with x cubed. Started with x cubed, reduce the degree by 1, and then factor this. This is going to become x minus 6 and x plus 3. Since we're trying to figure out what makes these the roots, these is really equal to 0. We're trying to find the roots. So x equals 6 and x equals negative 3 are the other two roots. How many roots are there altogether? Because?
It's a cube.
Very good. It's the third power, so you have at most 3 real roots. X equals 1, x equals 6, x equals negative 3 are your roots for this function. Or for this equation, I should say, not function, sorry. I want to do one last one, and this is what Tristan asked. Determine if something is a factor of something else. So what are you trying to find? If the remainder is equal to? 0. That's all you're trying to look for. Bring down the 2. Negative 2 times 2 is negative 4. Negative 4 is negative 8. Negative 2 times negative 8 is 16, and 1 is 17. Negative 34 and 7 is negative 27. Is this a root, or is it a factor, rather? No, because the remainder was not equal to 0. Hey, the last slide just goes through 2 other theories that we've talked about already. If the polynomial is x to the 5th, you could have at most 5 roots. That's the first thing it says. The second part says if you ever get something that has an imaginary part, the conjugate will be the other root. And we'll talk more about that theory also. We'll talk about both of these. Tonight, 8-5 homework, please. Tonight, 8-5 homework.
I know. He doesn't.
And then tomorrow. Oh yeah, it's never said it's not due till Wednesday. Did I put it through tomorrow? Yeah, I don't see you guys tomorrow, so homework is not due till Wednesday. Hey, start the round set so you don't have to really rough Easter break. A lot of questions, a lot of redundancy. Oh, we need to practice stuff.
Wait.
That's perfect, no problem. Yeah, that. You're welcome, guys. I need to get back. Wednesday's fine. What stroke? What stroke? Yeah, practice. We'll go through it. I don't know, we gotta find just those rules. Yeah, no one's ever had that. Wednesday. So there was something else it's done. They taking either a free count Miles off of a junior year. Miles in the end, it's the same thing. I've never understood why this chair. No one's ever done it that way. No one's actually taken Greek calc in the summer, it's Greek calc, basic geometry. Because we teach geometry, we are very specific. Three-quarters of the geometry, one-quarter of like logarithms and stuff. You're not gonna probably find the core stuff that anywhere in the summer. So you were gonna use a private instruction or something like that? That's what I was talking about. Your grades are good, right? You're good problem like that. So you might want to see you do geometry at really high grades before you get your permission. You know what I'm saying? Because geometry is a lot more. Pre-calc is a lot of algebra and a lot of geometry. So you got to do really well in geometry before you get to pre-calc. So he might want to do geometry here next year and then do pre-calc in the summer between those. It was still the same done. It would have involved this summer. That's usually the route that he takes. But ask him, he'll give you more feedback. Do you know what Salinas is? Okay.